Hello, I'm Sheldon, the author of Linear Algebra Done Right. This video discusses the section of the book titled Invariant Subspaces. Let's begin with a quick review of notation and terminology. F denotes either the scalar field R of real numbers or the scalar field C of complex numbers. We let V denote a vector space over F. Note that we only have one vector space now, rather than the two that we've been considering. That's because in this section we'll be working only with linear maps from a vector space into itself. We give such linear maps the special term operator. Thus an operator is a linear map from a vector space to itself. We also have special notation for such linear maps. We let L of V denote the vector space of linear maps from V to V. The reason for this emphasis on linear maps from a vector space to itself is that we can develop special tools for the study of such maps. For example, if we have a linear map from a vector space to itself, we can square it or raise it to a higher power. That will lead to interesting results, as we will see. To motivate our next definition, suppose T is a linear map from V to V. We will try to investigate T by composing the vector space V into a direct sum of smaller subspaces, and then looking at T restricted to each of those smaller subspaces. The notation used for the restriction of a linear map to a smaller subspace is shown here. The idea of restriction is easy. We are just reducing the domain of T to a smaller subspace. However, we will be developing some theorems about linear maps from a vector space into itself, in other words, about operators. If we want to apply those theorems to T restricted to a subspace U sub j, we need to make sure that T restricted to U sub j maps into itself. In other words, we're led to the following definition. Suppose T is a linear map from V to V. The subspace U of V is called invariant under T if whenever we take a vector in U and apply T to it, we end up with another vector in U. Let's look at some examples of invariant subspaces. Suppose T is a linear map from V to V. Then the subspace consisting of just 0 is invariant under T. The reason for this is that T of 0 is equal to 0. Our next example is the statement that the whole vector space V is invariant under T. That's because if we take a vector in V, then T of that vector is also in V, by the definition of T being a linear map from V to V. Our third example is the null space of T. The reason this subspace is invariant is because if we take any vector in the null space of T, then T of that vector is 0, which is in the null space of T. Thus T maps the null space of T into itself. Our fourth example is the range of T. If we take any vector in the range of T, then T of that is also in the range of T, and hence the range of T is an invariant subspace of T. Note that these four invariant subspaces are not necessarily all distinct. For example, if T is invertible, then the first and third subspaces are equal. The null space of T is 0. And furthermore, if T is invertible, then the range of T is equal to the whole space V, so the second and fourth subspaces listed here are invertible. Let's look at an example of an invariant subspace for a specific operator T. Our operator T will be defined on the vector space of polynomials with real coefficients. And we define T of a polynomial P to be the derivative of P prime. The subspace P4 of R consists of all polynomials with real coefficients and degree of most 4. This subspace is invariant under T because if we take a polynomial with degree of most 4, then its derivative also has degree of most 4. In other words, if we have a vector in P4 of R, then T of that vector is also in P4 of R. Thus P4 of R is an invariant subspace for T. Let's consider the simplest possible invariant subspaces. Well, the simplest subspace is the subspace consisting just of 0. But that's not very interesting and will not tell us any information, because if T is a linear map, then T of 0 is equal to 0. Thus, let's consider one-dimensional subspaces rather than just the zero-dimensional subspace. Suppose we take a vector v and v that's not 0, and we let u equal all scalar multiples of v. Then u is a one-dimensional subspace of v, and furthermore, every one-dimensional subspace of v is of this form. Suppose we have a linear map T from v to v. We can ask what it means for u to be invariant under T. Well, the vector v is in our subspace u. Thus, we need for T of v to be in u. But u is all scalar multiples of v. Thus, T of v needs to be a scalar multiple of v. With a little bit of thought, we see that our one-dimensional subspace u is invariant under T if and only if T of v is equal to some scalar multiple of v. We now have good motivation for our next definition, which is one of the most important definitions in linear algebra. Suppose T is a linear map from v to v. A scalar lambda is called an eigenvalue of T if there exists a vector v other than 0 such that T of v is equal to lambda v. The first time you hear this word eigenvalue, it may seem a little strange because the word is half German, half English, but you should get accustomed to hearing this word frequently. Now, let's look at some conditions that are equivalent to being an eigenvalue. Suppose v is a finite-dimensional vector space, and T is a linear map from v to v, and we have a scalar lambda. Then the following four things are equivalent. The first one is that lambda is an eigenvalue of T. The second is that T minus lambda I is not injective. Here I denotes the identity map from v to v. We can see why these first two conditions are equivalent if we look at the equation defining an eigenvalue. That equation is T of v equals lambda v. That equation is equivalent to the equation T minus lambda I applied to v is equal to 0. Since we are requiring v to be non-zero, the equation T minus lambda I of v equals 0 implies that T minus lambda I is not injective. Thus, we have the equivalence of the first two conditions shown here. The equivalence of the last three conditions follows from one of the important theorems we've previously discussed about linear maps from a finite-dimensional vector space to itself. That theorem said that the last three conditions are equivalent. Specifically, an operator from a finite-dimensional vector space to itself is invertible if and only if it's injective, if and only if it is surjective. Thus, we have the equivalence of the last three items. Let's look at an example to illustrate the definition of eigenvalue. Suppose T is the operator on R2 defined by T of x, y equals minus y, comma, x. This operator sends the vector 1, 0 to the vector 0, 1, and the vector 0, 1 gets sent to the vector minus 1, 0. If you think about it for a minute, you will see that T is counterclockwise rotation by 90 degrees about the origin in R2. It certainly does that on the two basis vectors just discussed. Now recall that an operator has an eigenvalue if and only if there's a non-zero vector that gets sent by the operator to a scalar multiple of itself. 90-degree counterclockwise rotation of a non-zero vector clearly never equals a scalar multiple of itself. Thus, we conclude that this operator T has no eigenvalues. Let's look at another example to illustrate the definition of eigenvalue. This definition also shows the importance of keeping track of what the scalar field is. Suppose T is the operator on C2 defined by T of w, comma, z equals negative z, comma, w. This operator looks very much like the operator in our previous example, except now we're operating on C2 instead of R2. Thus the variables have been called w and z instead of x and y. Notice that t of the vector 1, comma, negative I equals I, comma, 1, which is equal I times the vector 1, comma, negative I. In other words, t maps the vector 1, comma, negative I into I times itself. Thus I is an eigenvalue of t. Also, we see that t of 1, comma, I is equal to negative I, comma, 1, which is equal to negative I times the vector 1, comma, I. Thus t of 1, comma, I is equal to negative I times itself, which means that negative I is also an eigenvalue of t. You may want to pause the video and verify, using just the definition of eigenvalue, that this operator t has no eigenvalues other than I and negative I. We have defined the term eigenvalue. Now we need to define one more half-German, half-English word. Specifically, suppose t is a linear map from v to v, and lambda is an eigenvalue of t. Vector v in the vector space v is called an eigenvector of t, corresponding to the eigenvalue lambda. V is not equal to 0, and t of v is equal to lambda times v. Let's look at an example. Suppose t is the operator we saw on the last slide, on C2. T of w, comma, z is equal to minus z, comma, w. Then the vector 1, comma, negative I is an eigenvector corresponding to the eigenvalue I, because t of 1, comma, negative I equals I times that vector. We have now introduced two new words, eigenvalue and eigenvector, that sound somewhat similar. However, it's easy to remember which one is which, because eigenvalue is a value, meaning a number, it's a scalar, an element of whatever our scalar field is. An eigenvector is a vector, it's an element of our vector space. In this example, our eigenvalue is the number I, and our eigenvector is the vector 1, comma, negative I. When we have an eigenvector, then any non-zero scalar multiple of it is also an eigenvector corresponding to the same eigenvalue. You can see that easily in this case, for example. Suppose b is a complex number other than 0. We multiply both sides of the equation showing that t of 1, comma, negative I equals I, comma, 1, comma, negative I. We see that t of b, comma, negative bi is equal to I times that vector. Thus, b, comma, negative bi is also an eigenvector corresponding to the value I. This always happens by linearity. Now we come to an important result. Suppose t is a linear operator. The result says that if we have a list of eigenvectors corresponding to distinct eigenvalues, then that list of vectors is linearly independent. Let's look at the proof of this result. We'll denote our eigenvalues lambda 1 up to lambda n, and the corresponding eigenvectors will be v1 up to vn. Remember, we are assuming that these eigenvalues are distinct, and we want to prove that the corresponding list of eigenvectors is linearly independent. So suppose it's not true. This will be a proof by contradiction. Suppose our list of eigenvectors is linearly independent. By the linear dependence lemma, one of the vectors is a linear combination of the previous one. So let's choose k to be the smallest positive integer, making this true. Say that vk is the span of the previous vector says that we can write vk as a linear combination of the previous vectors. Now apply t to both sides of the equation, the bottom on the left-hand column, and use the fact that each v sub j is an eigenvector for eigenvalue lambda j, so t of v sub j is equal to lambda j times v sub j. That gives us the equation displayed here. Multiply both sides of the first equation, that's the one at the bottom of the left-hand column, by lambda k, and then subtract our two equations, getting the following equation. We have now written 0 as a linear combination of the vectors v1 up to vk minus 1. However, v1 up to vk minus 1 is a linearly independent list because we chose k to be the smallest positive integer so that we could write vk as a linear combination of the previous vectors. Thus Thus all the coefficients in the last equation must be 0. And because the lambda 1 up to lambda k minus 1 are all distinct from lambda k, this means all the a's have to be 0. But now, if we look at the equation at the bottom of the left-hand column, all the a's being 0 implies that vk is 0. But that contradicts our hypothesis that vk is an eigenvector. We call that eigenvectors, by definition, are non-zero. We've reached a contradiction, thus our assumption that v1 up to vm was a linearly dependent list is false. We therefore conclude that the list v1 up to vm is linearly independent. We now come to an excellent corollary of our last result. This corollary says that if we have an operator on a finite dimensional vector space, then it has at most as many distinct eigenvalues as the dimension of the vector space. Let's look at the proof. Suppose V is finite dimensional and T is a linear map from V to V. Suppose we have lambda 1 up to lambda m as distinct eigenvalues of T. But V1 up to Vm be corresponding eigenvectors. Our last result says that the list V1 up to Vm is linearly independent. But we know that any linearly independent list in a vector space has to have length less than or equal to the dimension of the vector space. That completes the proof. By the way, if you've previously taken a linear algebra course and you've seen a proof of this result using determinants, then you can see that this proof is much simpler. Determinants are complicated and not particularly intuitive. In contrast, this proof uses just the notion of linearly independence. This concludes the video on invariant subspaces. Hello, I'm Sheldon Axler, the author of Linear Algebra Done Right. This video discusses part 1 of the section of the book titled Eigenvectors and Upper Triangular Matrices. This video focuses on the existence of eigenvalues. Let's quickly review our notation and terminology. F denotes either the scalar field R of real numbers or the scalar field C of complex numbers. Let V denote a vector space over S. The word operator means the linear map from a vector space to itself. And L of V means L of V, comma V. In other words, L of V is a set of operators from V to V. We now need to define the powers of an operator T. If m is a positive integer, then t to the m is defined to be t multiplied by itself m times. Recall that multiplication of operators is really just composition of linear maps. Thus t squared, which equals t times t, is equal to t composed t. T to the 0 power is defined to be the identity operator I on t. And if t is invertible, with inverse t raised to the minus 1 power, then t to the minus m is defined to be the inverse of t raised to the mth power, as you see here. As an example of our definition, t cubed means t times t times t. Suppose t is a linear operator on V, then t to the m times t to the n is equal to t to the m plus n, and t to the m raised to the nth power is equal to t to the m times n power, where n and n are arbitrary integers if t is invertible, and non-negative integers if t is not invertible. You should be sure you verify these easy equalities. They follow immediately from the definitions. Now we need to define what it means to apply a polynomial to an operator. So suppose t is an operator on V, and p is a polynomial with coefficients in our scalar field F. If p of z is given by the formula shown here for each number z, then p of t is defined to be the operator that we obtain by simply replacing z with t. We also replace the constant term a0 in the polynomial with a0 times I, getting the equation shown here. For example, if P of z is equal to z cubed, then P of t is the operator t cubed. Let's look at another example. For this example, our vector space will be the vector space of polynomials with real coefficients. Let d be the differentiation operator of that vector space. D of a polynomial is equal to the derivative of that polynomial. Finally, let's take a polynomial p defined by p of x is equal to 7 minus 3x plus 5x squared. According to our definition, p of d is then 7 times the identity operator minus 3d plus 5d squared. P of d is supposed to be an operator on p of r. That means if we apply p of d to a polynomial with real coefficients, we should get another polynomial with real coefficients. That's shown by the last equation here. The polynomial that we get when we apply p of d to q is 7q minus 3 times the derivative of q plus 5 times the second derivative of q. That second derivative term, of course, comes from applying d squared to q. D is the differentiation operator, so decomposed d is the operator of taking the second derivative. Now I would like to discuss some of the algebraic properties of the map that takes a polynomial t to p of t. Here is the first of those properties. Fix a linear operator t on d. Then the function from the vector space of polynomials with coefficients in f to L of v, given by a polynomial p goes to p of t, is a linear map from p of f into L of v. This result follows easily from the definitions, but make sure you take a minute to verify it yourself. Our next result is similar, but it focuses on multiplicative properties. This result says that if t is a linear operator on v, and p and q are polynomials with coefficients in the scalar field f, then pq applied to t is the same as p of t times q of t. Let's work through an example to help understand why this important result is true. Suppose p of z is z plus 2, and q of z is the polynomial z plus 3. Then, just by using the ordinary multiplication of polynomials, we see that p times q, evaluated as z, is z squared plus 5z plus 6. We have that p of t is 2 plus ti, q of t is t plus 3i, and using the formula above for the polynomial pq, we see that pq of t is equal to t squared plus 5t plus 6 times the identity operator I. Now let's look. P of t times q of t is t plus 2i times t plus 3i, and then multiplying that out, we get t squared plus 5t plus 6i. And then looking at the equation in the left column, the last equation, we see that that is equal to pq of t. Thus we have verified that p of t times q of t is equal to pq of t in this particular case. But this case enables you to see why it's true in general. When we multiply the polynomial p times the polynomial q, we're just using the distributive property. And we do the same thing when we're multiplying p of t times q of t. In this case, t plus 2i times t plus 3i. The procedure for multiplying that and finding that product, just the distributive property, same is done with the polynomial. That's the reason that pq of t is equal to p of t times q.